Greetings to you all. In this lecture, we're going to continue our discussion of the mechanical behavior of materials, and today we will cover a couple of important characteristics of materials that relate to the time dependence of the failure phenomena. So we've seen before that we studied various numbers of problems. We looked at strength and cold work, and we also discussed toughness, resilience, and hardness and impact properties. And today we will focus completely on fatigue and creep phenomena. So for creep and fatigue, they relate to two different effects. One is continuous, where the load doesn't vary during the application. So this will be creep. So if we look at constant load, mostly, although in some cases the load can vary, but over a longer period of time. And usually this phenomenon is associated with long time behavior. The other phenomenon that we will also discuss is fatigue. And fatigue here relates to a variable load on the material where we have a time-dependent nature of mostly cyclic behavior that affects how the material feels. So let's look at creep. So creep is a phenomenon where if we have a sample, for example, here that has a load, and the load results in an axial strain. And the axial strain, in the simplest case, is uniaxial, but in general it could be multi-axial. So if I have a constant stress, so this is equal to a constant, and the stress is applied on the material where the material is heated at the same time. So this we have a heat environment where the temperature is high. So this is important to understand that in creep phenomena, they are associated with high temperature, where the material will undergo diffusion or plastic deformation due to the motion of dislocation. So there is a lot of motion happening inside the material. So if that material or sample is left over a very long period of time, then we would expect that the sample will deform, and the deformation will lead to substantial changes in the length of the sample. So if I have L0 to start with, then at any point in time, the sample length is going to increase, and it can increase substantially. Now that can produce large strains, and eventually we will get fracture localized in a region where the fracture is associated with grain boundary cavitation, where the cavities form on the grain boundaries and interlink, and they reduce the load carrying capacity of that sample. So that's kind of a general description. The deformation goes into stages, and generally we can describe it with 3 stages. So if we look at creep deformation on the vertical axis, and that is measured by either the length of the sample, or most likely by the strain that we can determine. So the strain, let's say if it is a true strain, it will be logarithmic of the length divided by L0. So assume that this is epsilon on this side, and if we plot this as a function of time, the strain initially increases, and it increases very rapidly. So we have an initial phase in which the strain increases very, very quickly. and that starts to decelerate. This increase decelerates, and we reach some kind of a balance, and that balance produces a second stage that can be different from the first stage. So the first stage, we're going to give it the Roman letter 1. The second stage, we're going to give it the Roman letter 2. And in this second stage, the slope of that line is constant. Slope is the rate of change of the strain with respect to time. So in this line here, epsilon dot is equal to a constant. And this stage usually is very long, and then at the end of that stage, the material becomes very, very long, and then we start having the cross-sectional area of the middle section of the sample decrease, and as the cross-sectional area decreases, then the effective or the local value of the stress become very large. And therefore, it's kind of a self-fulfilling prophecy, if you will. As the load increases, the cross-section will decrease further. And as the cross-section decreases further, the effective stress will increase once more. And that can lead to an acceleration of the strain, and that leads to stage 3 of creep deformation. So we discussed stage 1, where the elastic and plastic deformation, we have a decreasing creep rate. Due to strain hardening, the material starts to resist to harden, and therefore the very fast increase is kind of resisted by the material, reaching stage 2, where stage 2 we have a constant minimum creep rate that can exist for quite a while. And then finally that we can reach stage 3, where stage 3 the reduction in area becomes very significant, and eventually that leads to fraction. So let's kind of see stage by stage. So in stage 1 we call it primary creep, and during stage 1 with primary creep, the plastic strain recovery is less than the rate of strain hardening. So we have two opposing rates that the material has. One is recovery, where the dislocations start to annihilate one another and the material gets weaker. And the other one is strain hardening, where the dislocations multiply and the material tries to become stronger. So to the extent one rate or the other, that determines the strain rate. So we have, in this case, the plastic strain recovery is smaller than the rate of strain hardening. And therefore, the creep strain rate is a decreasing function of time. In general, failure does not occur in this stage, although if the stress is very high, failure can occur in stage 1. So if failure occurs in stage 1, we do not use the term creep rupture. We use the term stress rupture, because the stress is very high and causes rupture of the material. So it's a specific form of failure during creep deformation. Now in the secondary creep, this is the majority of design applications take place during that time, and in general that time can occupy 90 to 95% of the entire duration of the plastic deformation due to creep. And therefore, for most practical purposes, especially for power plant applications where we're talking about 20 to 30 years, we design generally for stage 2, where it's easy. We have the creep rate epsilon dot here is constant, and the constant, that constant is really not a constant. It is a parameter that depends on the temperature and depends also on the stress. We'll come to that in a little bit. So we will design generally for long-term creep on stage 2 deformation, and to specify stage 2, we designate epsilon dot. We give it the subscript s, so it'd be epsilon dot s for steady state or for stage 2. And during this stage, the two mechanisms that I mentioned, which is the hardening and the recovery, this is mechanism 1, and the recovery is mechanism 2, balance each other. So the material hardens and recovers at the same rate, and therefore we have a constant strain rate throughout the entire period. If we increase the temperature, for example, then we would expect that the creep rate will increase significantly, and again, if we increase the stress, the creep rate is expected to increase. So, looking at epsilon on the vertical and the time on the horizontal, and giving that we have a specific value of stress and temperature, we would get a rate of deformation that is shown here in the red curve. Suppose that we have the temperature, we fix the temperature, and we just increase the stress and repeat the experiment. What's going to happen in this case? The characteristic, the curve is going to, the creep rate is going to increase, and as we increase the stress further, the creep strain is going to increase following the third line that I showed here, and continually, if I increase the stress, we will have larger and larger amounts of deformation. So if I'm going to show an arrow, the arrow here is for increasing stress. All of that is done at a constant temperature as we increase the stress. You'll notice a couple of things, that the rupture point is getting smaller and smaller. So the rupture point here has a specific time, and this time we're going to call it T sub r. So this is the time to rupture, and that is also a design variable. A lot of times we would like to design for a given duration. For example, if I have a pipe, very hot pipe in a power plant, I would like to design it to survive for 20 years, but no more. So the time to rupture is, if maybe we will not design it to rupture, but we'll design it to be a fraction of that time to rupture. Let's say we design it to 80% of T sub r. So you notice as the stress increases, the T sub r decreases. Here's T sub r1, and here's T sub r2, and T sub r3, and so on. So as the stress increases, T sub r will decrease. And in fact, it can decrease so significantly that when the stress is very, very high, then we get into a situation where the stage 2 is totally eliminated, and most of the deformation is in stage 1. And if rupture occurs, in this case, then the rupture is called stress rupture rather than creep rupture. Finally, for the description of the creep process in stage 3, we get significant cavity formation on the grain boundary. So the grain boundaries, if these are the grains, then the grain boundary is going to form cavities everywhere, decorating the grains, as you can see here. and when they interlink, small cavities become very large, and the material separates along the grain boundaries and falls apart. And therefore, the load carrying capability of the material is reduced, and the strain accelerates to failure. And this is characterized by the time to failure or time to rupture, as I mentioned, and also a strain to failure or strain to rupture. Either we can use the subscript R or the subscript F to indicate failure or rupture. For design purposes, we specify a fraction of the time to failure as our allowable, or most often we specify a fraction for the rupture strain. For example, if the rupture strain is 20%, we specify only 1%, not 20%. So in the design code, the ASME design code, the epsilon allowable is equal to 1%, which is much smaller than what the material can take to rupture, because we want to have a very large safety factor. Usually the applications are very sensitive in terms of safety, and therefore we have to have a large safety factor. Now I describe the second type of time-dependent phenomenon, and that is fatigue. So under fatigue conditions, we have usually a stress that fluctuates as a function of time, and it can fluctuate between a maximum and a minimum, as you can see here. And then we have this is described as one cycle. So if there is a cycle that's applied, and we repeat that cycle from a maximum to a minimum, then the material, as we know, gets weaker and weaker as a function of time due to the formation of cracks inside, and usually the cracks go to the surface, and eventually the cracks propagate and you get what's called as fatigue failure. 80% of most of the failures that occur in design applications are fatigue failure. So to study fatigue failure, a simple device has been developed by this engineer, R.R. Moore, and in this design he developed a standard sample, and the standard sample has a length of 3 7/16 of an inch, and it's round, as you can see here. So it has two shoulders, and then the middle section is ground to a radius of curvature of 9 7/8 of an inch, and in the middle section the diameter is 0.3 inches. Now this standard R.R. Moore sample is embedded or included in a fatigue test machine that is known to induce stress reversal in the following way. We have ball bearings on these ends here of the sample, and the ball bearings induce a reaction force on this side and the reaction force on this side, and there's a load that is included, imposed on the material. So when we have a load on the material, constant load on the material and reactions, we obtain actually a moment, and the moment is distributed over this middle section. We can arrange the loading so that the moment on the middle section is constant. So we can have a 4-point bend test where the middle area has a constant load or a constant moment. Now, if I have this sample rotating, as it rotates and is bending under the moment, The top surface is going to be under compression, because if you can see my hand here, compression, and the bottom surface is going to be under tension. So each surface is rotating from top to bottom, and therefore each surface is going to go compression, tension on the top surface and on the bottom surface. That's very clever because we can rotate the sample very, very quickly, let's say 5,000 RPM, and therefore we can get 5,000 cycles, fatigue cycles on the surface of the sample where we have the stress fluctuating from large to small, and so forth. And then we do this test for a specific number of cycles, and then we plot the stress here, S in KSI, as a function of the number of cycles to failure. So this plot, we have a log to the base 10, plotted as a function of log to the base 10 of the number of cycles to failure, and this is log to the base 10 of the applied stress amplitude. So we have, of course, the stress is varying as a function of time, but the amplitude is what matters. The amplitude is this value here, and this is sigma applied, or S, that we will record. So when we have S on this side, recorded as a function of N in log, we will get an SN curve, and the SN curve has 3 stages here. In this range here up to 1,000 cycles, we term fatigue to be low cycle fatigue. Above 1,000 cycles, we call it high cycle fatigue. And then when we get to about 1 million or 10 million, anything above that, we would call it infinite life. So we'll go into the characteristics of the SN curve later on in the course. For now, we understand now that if we apply a certain amplitude, then the number of cycles will accumulate until we get to a point that there's going to be failure. In this case, let's say at 2 times 10 to the 5 cycles, we get fatigue failure. And this is an example of an SN diagram for steel where any number of cycles below 1,000 is called low cycle fatigue. Anything above 1,000, we call it high cycle fatigue. And with that, we will finish our lecture on fatigue and creep, and we'll see you on my next video.